let's prove the following statement using the principle of mathematical induction. So let's remind ourselves, what is principle of mathematical induction? It's going to be an induction on the natural numbers or positive numbers. And the first thing we want to do is show that the proposition of the initial step is true. Then we're going to suppose that the proposition of k is true for some fixed k. And from there, if we could knock over the next domino, in other words, if we could prove that the proposition of k plus 1 is true, then we could actually conclude that it's going to be true for every k after that. Okay, so why don't we try that? All right. First thing we want to do is write the word proof. And we want to show proposition of 5. So why don't we start with 4 times 5? And we're going to observe that expression. What is 4 times 5? Well, we know that is in fact less than what? We know that is actually less than 32. And what does 32 equal to? 32 is equal to 2 to the 5th. Well, therefore, what can we say? 4 times 5 is less than 2 to the 5th. And that is true. In fact, that is proposition of 5. Therefore, proposition of 5 is true. So we got our initial step. How did we know to start with 5? It says so. K is greater than or equal to 5. Now let's suppose piece of K, or proposition of K, is true for a particular K. And so what do we mean by particular K? You could envision that it is actually fixed. Okay, and this K, of course, is somewhere greater than or equal to 5. Okay, no, it's actually not 5. It's going to be greater than 5. So what does this mean? This means four times K is less than 2 to the K. And for now, we're going to envision that this K is fixed. Now, what do we want to show? We want to show that the proposition of K plus 1 is true. In other words, we want to work out this expression, 4 times K plus 1. And eventually, we want to show enough work. We'll figure out what those 3 dots mean. Eventually, we want to conclude that this is in fact less than what? 2 raised to the K plus 1. So that's what we're working on. Let's see. All right, so why don't we observe 4 times K plus 1? So why don't we note is another way of saying observe. 4 times K plus 1. And what are you tempted to do? Well, you're tempted to distribute that. 4 times K plus 4. Well, what does that mean? We know 4 times K is less than something. In fact, that's got to be less than 2 to the K. And we still have a plus 4. Well, if you observe that, carefully, we know that 2 to the k plus 4 is less than 2 to the k, let's say plus 4 times k, right? Because k is a positive integer that's more than 5. Well, why don't we use the less than assumption again? So now we know this is less than something. That's in fact less than 2 to the k plus another 2 to the k. That's pretty cool. Well, we know that's equal to something. That's actually just a like term, and we have two of those. 2 times what? 2 to the k power. But what is that equal to? That is in fact equal to 2 to the k plus 1 with your rule of exponents. That's pretty cool. So what just happened? You just showed that this part here is in fact less than that amount right there. That is in fact the proposition of k plus 1. Therefore, 4 times k plus 1 is less than 2 to the k plus 1. Therefore, proposition of k plus 1 is true. So what is our conclusion? By the principle of mathematical induction, we'll abbreviate it PMI, 4 times k is less than 2 to the k is true. Now we just changed two words. We need to add the two words for all. Emphasis is on all. K greater than or equal to 5. Now remember, in a proof, your solution is not the last line. Your solution is actually the entire proof. So we're going to circle the entire proof. So a lot of times you're accustomed to circling the last line, but in a proof, you're going to circle the entire proof. That's what's needed. Make sure you put everything in order, dot your I's and cross your T's, and don't skip any steps.